Welcome back to this course on multicore systems. The protocols that maintain coherence in shared memory multiprocessor systems are called cache coherence protocols. There are different classes of protocols in use, as will be explained in this lesson. The protocols used to maintain coherence in multiprocessors are called cache coherence protocols. Roughly speaking, at a high level, there are two different kinds of cache coherence protocols. The first is Snooping protocols. In such protocols, the cores, or more precisely the cache controllers, snoop or monitor the bus. If they discover that they have a copy of the cache block whose address is being broadcasted on the bus, they should react in a certain way. Snooping protocols requires that the address of the block that is read or written be broadcasted to all cores and therefore work well with the bus. Snoop protocols are mainly used in relatively small systems, consisting of up to, let's say, 8 cores. The second class of cache coherence protocols are the directory-based protocols. In these protocols, the sharing status of a memory block, meaning which caches have a copy of it, is kept in one location called the directory. Directory-based protocols scale better than snooping protocols and are therefore mainly used in large shared memory systems. In this lesson, I will focus on snooping protocols, the first. The next lesson covers directory protocols. Snooping protocols can also be divided into two types of protocols. The first are the Write-Invalidate protocols. These protocols are called Write-Invalidate because they invalidate all other copies on a write. This table illustrates what happens in a Write-Invalidate protocol. Initially, the contents of memory location X equals 0. Then processor PA reads X and fetches a copy of X in its private cache. And after that, processor PB also reads X and fetches its own copy of X. Then processor PA writes a new value of 1 to X. It writes this new value into its cache, but it also invalidates the copy of X in the private cache of processor PB. Finally, processor PB again reads X. It will not fetch it from memory, but fetch it from the private cache of processor PA, since that cache contains the most recent value of X. Also, the memory copy will be updated. The second type of snooping protocols are the write-update or write-broadcast protocols. These protocols do not invalidate all other copies, but update them on a write. This table illustrates what happens in a write-update protocol. The first two steps are the same. Processor PA and processor PB both get a local copy of X. But now PA writes 1 to X. Instead of invalidating the other copy, it updates them, both in the cache of processor PB as well as in memory. The subsequent read of X by processor PB will then be served by the private cache of processor PB. Let's now try to qualitatively compare write-invalidate protocols to write-update protocols. When a processor repeatedly writes the same word, then write-invalidate require only one invalidation, whereas write-update will require multiple write-updates or broadcasts, since every time all copies need to be updated. Similarly, when a processor writes different words, but these words are contained in the same cache block, write-invalidate will again require only one invalidation, while write-update will require multiple write broadcasts. On the other hand, the delay between writing data in one core and reading the new data in another core takes longer in a write-invalidate than in a write-update protocol, since it first requires an invalidation and then getting the new data. So we can conclude that write-update protocols consume considerably more bus bandwidth than write-invalidate protocols. And for this reason, recent multicores implement write-invalidate protocols. Therefore, I will focus on write-invalidate in the remainder of this lesson.
This completes this lesson. Thanks for watching. In the next lesson, I will present an example write-invalidate protocol called the MSI protocol. Hope to see you back.